We've had lots of delays on our ESCs, just kind of been tuning them, trying to get them perfect for everyone. We just haven't been happy with the performance. One nice thing that happened during this process is a new tech from BL Heli had come out, and we were able to be the first one to incorporate this into our ESC. Not only did we incorporate one thing that no other ESC in our hobby has done, but we actually were able to incorporate multiple things into the new design that, dare I say, makes it the best ESC that has ever been used in our mini quads in our hobby. So, first thing I'm going to show you here on this screen, this is a very good video. I was looking for some videos to figure out the best way to explain to you how ESCs worked. And I think this video does a really good job to explain exactly how our motors are driven and how ESCs work. So I'm going to link this one in the description, but I'm going to use it to give you a quick rundown of why I think exactly how the ESC works. And then I'll try and explain as simple as I can why I think ours is better and what it does differently. So a quick rundown is, if you look at this is a great picture of a motor. And again, check out this video because he goes into a lot more explanation than I'm going to, and it's a really good video. But basically the way it works is you have electromagnets on the outside and magnets on the inside. Our motors are opposite of this. They have the magnets on the outside and electromagnets on the inside, but the principle is exactly the same. This one needs gear reduction to be used better if it's this design, but with us direct driving the props, the opposite design should work a little better. So basically the way it works is you have magnets that are one polarity one way and one other polarity the other way, and you have these electromagnets on the side. So what you're doing here is you're triggering individual electromagnets that are opposite of each other to the opposite of the pole of the magnet on the stator, or on the outside of the motor in our case. So what that does is it pushes it away because they're opposites, so they try and push. And at the same time, you're firing the opposite magnetic poles adjacent. So one way you're doing the same, which makes them repel, and the other way you're doing different, which makes them attract. And so some pull while the others push, and that's what spins the motor. The third one doesn't do anything. It's left dead, and that's usually used for sensing, so you know the position of the motor. So if you look here, you can see here he's illustrating that basically one magnet's one way and another's the other way. But we do something with our other motors, is we do some sort of sensing here on the opposite pole. And that lets us use, basically, magnets can produce magnetism, or if you run electricity through them, or if you run magnets through one that doesn't have electricity, it creates electricity. And we use that electricity to get the position of where it is in the motor, and that's what's responsible for the startup. And that's why, like, if you have RC cars and you have a sensored motor, it works a lot better at starting up. Our quads are very bad at starting up the motor. But it doesn't have a lot of weight, so it's not as big an issue as like a car, which is trying to drive the car forward. But you use these sensors, and basically there's a sensor on each pole. We're divided into 3 phases. That's why our ESCs have 3 wires each. One is used as ground, one is used as power every time you energize it, and then you can use it to sense as well in the same way. So what we do is we run this voltage into something called a comparator. And what a comparator does is it is a trigger that when it hits a certain voltage, it triggers and notifies us basically it hit that voltage. You set a comparator to a certain voltage, and when it triggers, that's how it works. And our MCUs basically have one built-in comparator, but we have 3 phases. So basically all the phases have to share the same comparator. And so when the comparator triggers, they're all tied together, then the ESC has to go, and it has to actually pull another pin that's connected to see what the power is and which one triggered. So traditionally, this is the way our BL Heli 32 and our BL Heli ESCs work. It uses the one comparator on the CPU, the MCU, and it pulls one of the 3 wires to find out, what's going on. Some issues with this is it's noisy. Our CPU is really noisy. It runs at high megahertz, which creates a lot of noise. Not only that, but we have to actually pull stuff. We have to reset up stuff. So it's a good solution, but there's a better way to do it, and this is the way it's been done for since I've been flying quads in this hobby. And I'm not aware of any other ESCs that we use that do this differently. I mean, maybe KISS does. I don't know. I don't think they publish exactly how they do things. But I'm assuming they use similar tech to this because it's pretty standard. One thing we found, there's two types of MCUs everyone uses. They use the F3 Chinese MCUs, and they use the F0 American MCUs. Now, one thing we've noticed with testing, and one of the problems we've had is honestly these Chinese MCUs, the comparators are bad on a lot of them. So we have to basically test every MCU we get, find the good ones, and not even use the bad ones. We can use them on other projects, which I think our manufacturers tend to, but on the actual ESC where we need a comparator, they're unusable. So we end up, that's a step we have to do. And not only that, but they're bad with noise. We had some resetting issues. If the ground plane gets too noisy or whatever, they tend to reset, and the American, the STM F0 MCUs don't do that. You think faster is better, and that's one of the reasons we use the F3, but it's not that much faster. It has a lot of downsides, and with the new code, we're running DShot 64, which is DShot 2400 for those of you that follow the Betaflight naming scheme. So it allows 64 kilohertz worth of signaling back and forth, essentially. That's why we called it DShot 64. So there's no downside to using the American MCU over the Chinese MCU. To us, there was only upsides. So the first thing we did is we went all American. All our ESCs are now using American MCUs. They work better. They have better sensing. They have better everything. The only thing is they're a little slower, but we don't notice that because we're with the way the BL Heli-32 is written and everything. They're 64-bit, 20 DShot 2400, no issues. So the next thing we did is the way the sensing works. If you look here, we actually use something called an external comparator. Now this is pretty exciting because basically our MCU has one comparator on it. It has one thing that can do the sensing. And like I said, we have to share that thing and then actually read the voltage every time it triggers. And it becomes, it's not the best way. And the voltage can be noisy as well because it's built in the CPU and the sensors don't work as well. So with this external comparator, we have 3 of them now. So we have one for each wire. And the external comparator is amazing because it actually just triggers an interrupt. Instead of us having to read voltage, it just triggers an interrupt in our thing. And what an interrupt does is it basically is like a notification. It's like a light switch. It's like when you get a message on your phone. It tells the MCU, bam, it's the voltage you want it to be. This is much more reliable. And not only that, but now we know exact position of each of the 3 phases at all times, which makes it better for starting up. It makes it smoother running. You're going to notice the ESC is even smoother than any ESC you've seen. Desyncing issues are less prevalent on this because it always knows the position. And all a desync is it doesn't know the position of the ESC when something happens. So it's just trying to recover to get the position back. And so this helps with that as well. So using that, it's very good tech. It helps us make the smoothest ESC ever made. And we're pretty excited about that. So the next thing we did, these ESCs, we've always had people put on external caps, but when you put them on, they're hard to mount. The length of the wire actually hurts the performance of the cap. So for every millimeter the wire is longer, the ESR goes down, and the ESR is the resistance, and the less resistance, the better it works. What a cap does is it basically is like a super fast battery. So when your ESCs are pumping those motors, they're turning them on and off really fast. They're turning them on and off at 48 kilohertz, so 48,000 times a second. It's creating deficits in the power. So basically, if you can imagine, there's peaks and there's valleys, and every time it triggers, there's a valley, and we want to fill that in with power to keep everything else powered. So we add external capacitors and we add surface mount capacitors to help with that. The big external capacitors help. They definitely help. They cut down noise and other issues, but they're not the best solution. So we found these Panasonic. Panasonic makes the best caps that we've ever tested. And their FM series is just amazing. So if you need a cap for your quad, FM series, Panasonic's the way to go. We found if we move the pads out just slightly, and you can see this in the image, we were able to fit the caps right beside it, these caps, and still have the flight controller mount perfectly. So These caps are going directly in the circuit. They're better caps than if we had surface mount ones. And they just work amazing. So this is another thing that helps with smoothness. So we've replaced the freestyle ESC with this one. We're probably gonna use the same, we're using the same design on the other ones as well. Just similar things, but it just is even smoother. We had the cap board in the middle. This is just way better than even doing that. That with the 3 external comparators and then even more stuff, it's a better ESC all around. The next thing that we've even done too is now we can drive the ESC output at 96 kilohertz. That's pretty exciting too, because like I said, when it's pulsing the power, it's basically pulsing your motors, you're dropping power in the entire system. So the more times we can pulse it and the lower the pulses, so basically we suck less power each time, the more stable it makes the power in the system altogether. So what that's going to do is make your gyro readings cleaner, make your video cleaner, and make the ESC feel smoother, because little pulses are better than big pulses. Our ESCs aren't sine wave ESCs, which basically a sine wave starts low, goes up, and goes back down. Ours just basically full power, full power off, full power on, full power off. So making those pulses smaller, the full power on, full power off, give us the smoother feeling. It may take a little bit of power, so if you're worried about absolute peak power because you're just top tier racer and you don't need smoothness, you can lower that if you feel the need. But in general, it works the best. And the other thing we've noticed too is we've liked synchronizing the output of 32 kilohertz to match our gyro. But even though that syncs, which helps with some aliasing, we find that 48 kilohertz can be a little smoother because it makes the power smoother. However, 48 kilohertz isn't even multiple of our 32 kilohertz, so I feel like it causes some aliasing, and I know some people probably argue that. But 96 kilohertz is the best of all worlds, because not only is it smaller, but it's a 3 times multiple of our loop speed, so there's no aliasing there at all. So basically, I think it synchronizes just perfectly, and it just makes for the perfect ESC output. Other than that, they're pretty robust. We have no other issues. These are in the wild already. We have a lot of people with them. We're going to catch up on everyone's ESCs now that we know this design's solid and it's perfect. So just be watching for your shipments if you don't have them yet. I'm going to put a list of the vendors we've already shipped these to. So if you want to pick them up, but they're going to be, I almost guarantee, the best ESC you've ever tested in our hobby. If you have any questions, please like and comment and ask them in the comments. I probably didn't do this justice on how exactly an ESC works, but I recommend you check out some videos I've linked and ask some questions, and maybe I can get to the bottom of any questions or details that you guys are asking and make you understand even more. I know this was a more complicated subject, and I'm hoping I'm doing it justice and doing a good job of explaining it. But if not, give me some suggestions of what I should do next time, and feel free to ask me any questions. Oh, one other thing I forgot before we left, we changed the size of the wire connectors on them. So basically we used 1 millimeter pitch wires, which we found were more prone to noise and couldn't carry as much current. So now we're upping the size to 1.25. We're going to start doing that on all our flight controllers in the future, but that should give a more solid connection. We're also running multiple grounds, which makes sense because if we're running power and all our signals use the same ground, multiple grounds are better, so we're doing that as well. One thing you can do is you can wire the external ground, just solder to your flight controller anywhere if your harness doesn't support it, which our current ESCs or FCs don't. I think that about summarizes it. If I missed anything, hopefully I'll catch it in the next video. And if not, look for posts on our Facebook group and let me know any questions you guys have.